Even though I love tinkering with FPGAs, I never really went into PCB design. Maybe you're like me and you're looking to do a first PCB design that is not too simple so you can impress your family and friends. They do not care. They do not care one bit. Or you simply want to impress them LinkedIn recruiters with something that looks tech enough so you can get hired. Lucky us, Phil's Lab just released a 2-video tutorial on how to make a PCB with 2 layers packed with stuff like a UART to USB converter, an I2C accelerometer, and an MCU. Yeah, actually that's all there is to it, but in this video we'll review the project and we'll discuss some points I think Phil missed in his videos, and especially one that will make you save tons of money. I mean, it's not tons of money, but it actually saved me like $100 to $150 or even more depending on the method you used. So yeah, it's kind of worth it. We'll also see how to actually program the end product, because if you're watching this video, you probably don't really know how to tinker around with complex embedded systems, which is fine. And I guess Phil should have discussed this in his videos, but he didn't. But it's okay because this allows me to yap about it in my video, so... Okay, so first of all, the design process review. The goal here is to create a PCB design with little to no notions in PCB design. So we get taken through the whole process in TCAD. At first we start with the schematics, of course. Like, putting components together. You'll still need some electronics knowledge, but it only goes as far as knowing what a decoupling capacitor is, and it's fairly easy to learn. The datasheets and Phil's Lab got a back on this, so you don't really have to calculate any value, you just have to place the capacitors, which is kind of fairly easy. But once you lay your components down on the schematics, you can either put them on a breadboard, but because we are grown men, we are going to make a PCB prototype directly out of it. This is where the fun and fancy part begins that everybody is waiting for. It's routing. The routing process when you create a PCB is kind of the process that everyone thinks about when thinking about PCB design. It's kind of like creating a piece of art, and it's actually pretty fun. I mean, it's always fun until the people that are smarter than you and me start talking about impedance matching or crosstalk or whatever. And because the lion does not bother himself with boring engineering principles, we'll just ignore that it exists for now. Anyway, now that we have a pretty good looking board, comes the ordering process. This is the moment where you have to spend some minutes trying to make your bill of material work on the manufacturer website and have to pay, which is not my favorite moment, I gotta admit, but you have to pay up at some time. This is also the moment you gaslight yourself into thinking that everything is fine and that your PCB design will surely work. I was pretty sure it will not work, actually. I also decided to order the USB-C port and the 6-pin header separately because they were not really falling into place in the EDA visualization online. So I figured just adding some badly soldered slop on top of the already not that great PCB design wouldn't really make a difference at this point. Speaking about the 6-pin header, let's address the elephant in the room. Phil made a whole speech about this connector that is easy and cheap to manufacture. But what he forgot to mention is that the cable, just the cable, to interface the debugger with this weird footprint is actually $30 to $40, which is a lot of money for a brokey like me. And the actual debug probes cost $100 or even more depending on the brand you use, which is not that much of a money for a business, but for a hobbyist, it's definitely a budget. God damn! Anyway, I was not having it this way, so I decided to order some 6-pin headers and use a standard 6-pin header for this matter. Don't worry, I'll just go over how I debugged the chip using a 2 to 3 euros debugger. But we'll get to that later on in the video when I'll tell you how to actually program the chip. At this point, I have to admit, I kinda ordered this thinking it wouldn't work, and I just wanted to gain, the experience to be better at my everyday job, and I just felt dumb not to be able to know how a PCB works. With that being said, once the PCBs arrived, I was very excited. My first PCBs, bro. So happy. Alright. I told my family. I was like, whoa, look at my PCBs. They didn't care. They didn't care at all. But I was still excited about these little PCBs. So the day after that, I got to actually solder the USB-C and 6-pins header on the little PCBs I just received. Oh shit. And after inhaling way too much flux and lead vapors, I was prone not only to cancer, but also to success.
Better call Saul!
As the board was now fully assembled and allegedly able to run stuff. Before moving on to actually applying power to this board, I checked every continuity and every shorts possible on the board like a psycho. The reason why is because I was convinced it wouldn't work and that as soon as I applied power to this board, it would spontaneously combust. Did I say it right? Spontaneously, yeah, that's the word. Miraculously, it turns out there was no real obvious problem, so I courageously plugged a USB-C cable onto this board. And it worked. It actually worked, which is not expected, but it did, so I'm happy about it. And the board was not getting hot either, it was not showing signs of anything actually, so it was a good sign. But when you plug it in like this, it does nothing, which is expected. We did not even put LEDs on this PCB. So how do you actually use this chip to make it run a program and use the accelerometer on board? It's not like an Arduino. As I said before, the USB-C cable you plug in can only receive and transmit UART signals to the MCU. Nothing else. This does not let you program the chip or do anything fancy. The solution is to use a debugger. You know, the $100 component I talked to you about earlier. The debugger can take control of the chip at any time. It can put it into a reset state, access peripherals in the SoC, blah blah blah, you know, it can do many things. But most importantly, it can flash a program to the chip. But as I said before, we did some shenanigans with the footprint that feels like suggested. That means we are kinda on our own for the debugging solution here. So how are we going to debug and flash a program on this chip? Well, good thing the Chinese got our backs again on this matter. The TI MCU, the MSPM0, uses a standard debugging protocol called single wire debugging, which is not proprietary at all. Did I spell it right? Proprietary. I struggled in the Holy Core video to say this word also. Is my English getting any better actually? I don't know. But yeah, because it's not proprietary, Chinese got our backs and they made some pretty low-cost debuggers for us, which makes us brokies and hobbyists very happy. And it turns out a simple ST-Link debugger, which costs €2, has a single wire debugging interface feature. So after wiring up your debugger to your chip and plugging it into your host computer, nothing happens, which is normal. And that's because you have not heard about one very useful and powerful tool. It's OpenOCD. Basically, it's a piece of software that can recognize most of the debuggers on the market, take control of it, and use its interface, in our case the SWD interface, to take control over the MCU and do stuff like load a program, blah blah blah, you know, what we actually want to do. All you have to do to use OpenOCD is install it, give it some config files, and boom, you can talk to your MCU directly to debug it. If you want to learn more about OpenOCD, how to install it, and some guidelines, I'll leave you some material in the description. And on the front end, it simply opens a GDB server, which sounds complicated, but it's really not, and GDB is a widely known debugger you can use to load program and debug program, which makes it more than just a program loader. Okay, now we have a stable debug connection to our MCU. But still does nothing though. We need a program to run, of course.
Why do you suppose I just hurled a chair at your head, Neiman?
To do that, we'll use TI's IDE called CCStudio. Just a side note, I was not really able to run it on Linux, so I used my trusty unactivated Windows 10 virtual machine. To create a binary able to run on this MCU, you have to create a new project, specify our part, and compiler that you can install on Windows via the guidelines in the description, and choose an example project. Because I provide some code, you can choose to create an empty project, but you can also tinker around with an I2C or UART example project. Then you have to configure the target by specifying which model of MSP M0 you are using, which package, and specify what UART pins you are using and what I2C pins you are using so the drivers don't mess up the IO's stuff. Once this is done, you can write your code, which is something I'll let you handle on your own, or you can simply copy and paste the code I'll leave in the GitHub repo in the description, which is simpler, not gonna lie. And once you're ready, you can compile it. And if it works, congratulations, you now have an ARM binary ready to run on your MCU. To run this program on the MSP M0 MCU, you'll need to install a multi-arch version of GDB, which I'll also leave some guideline in the description to do so. Once this is done, open gdb-multiarch, specify the path of your binary using the file command, and connect to the OpenOCD server you previously launched via OpenOCD using the target remote command. Then run load to load the program into the target's memory and run continue, which will execute the program. The program shall now be executing. But how do you know it's executing? Well, the example program I gave you in the description sends UART data to the host PC. So you can just open a TTY UART terminal to check if you actually receive the text information. And GG, you did it. You shall now see in your UART terminal sensor information coming from the MCU, and this information is communicated to the host PC via UART. I also made a small Python script that visualizes it as a nice vector, which makes the project kinda nicer. Alright, I hope this video was useful to you and that it was a good complement to Phil's Lab series of video on PCB designs for beginners. If you liked it or found it useful, you can always leave a like and comment. It really helps the channel more than you think. With all that being said, thank you for watching and I'll see you in the next one.